It's working? Mm-hmm. Okay. So it's my pleasure to welcome Jonathan Gruber to give his second talk on minimal tilting complexes and tensor products for algebraic groups.
Okay, thanks for the introduction, and thanks for coming back for the second part. So last week I told you about the concept of minimal tilting complexes in a highest weight category. And this week I want to show you how you can use it in a concrete example of a highest weight category to study sort of additional structures like tensor products. More concretely, if we look at, say, G, a simple algebraic group, for example, if you want to think of something concrete, we could take G to be the group of, the special linear groups of matrices with determinant 1 over a given field, and we assume that K is algebraically closed, and the characteristic of K is a prime. Then we have a category rep of G of rational representations. Which means that I'm looking at representations of the group, which are at the same time group homomorphisms into some GLN, but they're also morphisms of algebraic varieties, because this algebraic group, the defining thing is sort of it's a group, but it's at the same time an algebraic variety, and the two structures are compatible with one another. So this is the kind of representations they want to look at in this category, and they want to look at the finite dimensional ones. Okay, so this, the main point of what I'm saying here is that this here is going to be a highest weight category. But it also has a monoidal structure. So whenever you're looking at representations of a group, you can take the tensor product of two representations, take a representation in every way. So this here is also the tensor category. And now the aim of the talk today is to explain how we can sort of use the highest weight structure of this category in order to study the tensor product, so the monoidal structure. And the tool for doing this is going to be the minimal tilting complexes that we just get from here to here by the minimal tilting complexes. Okay, so first, I wanna tell you some things. This is the one representations. I want to tell you some things about representations of G, and I want to remind you of what a minimal tilting complex is. So first, so this group that we're looking at comes with some data. Namely, we're going to have a root system associated to G. Which is going to be sitting inside some Euclidean space, and between the two we have the weight lattice of the group, weight lattice, and a Euclidean space. And then within the root system we can fix some positive system. And we can fix the base of the root system, define a positive system. So we the base, and we have a positive system. And now, from the positive system, we can also define a set of dominant weights, x plus, sitting inside x, and that's just the set of all lambda in x. Such that the scalar product with all co-roots for positive roots is greater than 0. Okay, so alpha 5 plus. These are the dominant weights, and there's a canonical partial order on the weight lattice, which is defined by saying that for lambda and mu in x, we say that mu is less or equal than lambda if and only if the difference between the two is a non-negative integer linear combination of simple roots. So this should be an element of some 0 set greater than 0 alpha, where alpha runs over all simple roots. Okay, so now we have a set and we have a partial order, and together these are going to be the weight core set for our highest weight category. So set rib of G is highest weight category with weight core set x plus and this or equal. And as I explained in the last talk, what this means is that we have objects, canonical objects, indexed by the set of dominant weights. Namely, we have the simple objects L lambda, so the simple G modules. Then we have standard modules delta lambda. We have co-standard modules nabla lambda. And we have indecomposable tilting modules. Tilting for lambda and x plus. And I just want to say a few words about these. So the simple modules, it's fairly easy. These are the simple objects in the category. And I explained last time that essentially the standard objects have the simple object of highest weight lambda have the unique simple quotient, and the co-standard objects have them as their unique simple sub-object, like Verma modules, if you want to think about category O or dual Verma modules. And so this is sort of in the notation, it's reflected in the fact that this is a triangle that has sort of a unique thing sitting at the top, or a triangle having a unique thing at the bottom. Tilting objects are defined by having a filtration by different standard objects, but also a filtration by different co-standard objects. And for each highest weight, there's a unique indecomposable tilting object of that highest weight. Every tilting module is going to be a direct sum of those. Okay, all of this I already told you last time. In this case, maybe something that is useful to know is that these modules can actually be obtained by inducing a one-dimensional module from Borel subgroup. So every weight defines a one-dimensional representation of Borel subgroup, and you can induce it up to the entire group. You get something non-zero if and only if the weight that you started from is dominant, and these are precisely the co-standard modules that you get. Get the standard modules, you can get them by just dualizing the co-standard modules, because you also, for group representation, you can also always take the dual, you get a representation again. All right, that's essentially, that's almost all we need to know about these representations, except there's one additional thing that's going to be absolutely central for this talk. And that is that let's say we write tilt of G for the subgroup of tilting modules. Tilt of tilting modules, and this is closed by tensor products. So this is a very important theorem of Steve Donkin and Olivier Mathieu. So it was first proved for almost all primes and root systems by Steve Donkin, then it was proved in the completely general case by Olivier Mathieu using Frobenius splitting. And this theorem is going to be exactly what is going to make the strategy of using minimal tilting complex to study tensor products. This is what makes the entire theory that I'm going to talk about tick. Okay, so this is sort of general stuff about representations of algebraic groups that you need to know. And now let me just remind you of what is a minimal tilting complex. So if we have, say, M G module, then by definition, the minimal tilting complex C min of M is the unique minimal bounded complex of tilting G modules such that if you take the cohomology of that complex, so you take Hi of C min M, then in degree 0 you just recover the module that you started from. So it's going to be isomorphic to M. If you take I equal to 0, it's going to be 0 everywhere else. Okay. All right. So, and this, so as I told you last time, essentially this cohomology property here determines the module unique up to homotopy equivalence. But if you additionally ask that the complex is minimal, so that there's no redundancy in its differentials, then this is actually going to be unique up to an isomorphism of complexes. But there's a nice additional effect, which is that, so if you take a bounded complex C of tilting objects, which satisfies the same cohomology condition, so Hi of C isomorphic to M I equal to 0 and 0 if I is not equal to 0, then as I've just explained, that means that the complex C belongs to the same homotopy class as the minimal tilting complex. And in the last talk, I explained that once you have a complex in a given homotopy class, you can sort of run this process of Gaussian elimination on complexes and go down to a minimal one. Mm-hmm. And in the process, you sort of split off redundant direct summands of the complex. So that means that the minimal tilting complex in this homotopy class is actually going to be a direct summand of this complex that you started from. Okay, so then C is a direct summand. No, sorry. The minimal tilting complex, C min of M, is a direct summand of C. Okay, so this is one remark, and then the second remark to make, I'm just going to use this diagram which I drew ahead of time. This is going to be, so I want to explain what exactly is the reason why we can use minimal tilting complexes to study tensor products. Okay, and essentially the reason is that they're somehow compatible with both direct sums and with tensor products. So firstly, so let's say we're given M and N two G modules, then first it's fairly easy to see that if you want to have the minimal tilting complex of the direct sum of the two, you can just take the direct sum of the minimal tilting complexes. Okay, so I mean the cohomology condition is going to be satisfied on the nose because cohomology sort of commutes with direct sums, and then the minimality is also fairly easy to check because you just write the differentials next to each other, nothing happens there. And so secondly, when you're given any two complexes, there's a definition of a tensor product complex. I mean, at least as long as you're looking at complexes of representations of a group. So you can define a tensor product complex C min of M tensor C min of M, and its terms are going to be defined by, so if you want to have the term in degree k, then you take the direct sum over all the terms in degrees I and j that add up to k. So we take direct sum over all I and j, whose sum is k, and we take the tensor product of Cmin mi tensor Cmin n j. So this doesn't tell you the differential, but where the differential comes from is essentially if you want to find this tensor product complex, what you do is you look at a double complex that is defined by the two complexes and you take the total complex thereof. And what I mean by this is basically so if you look at this diagram here that I drew, if you look at each fixed line, you'll see that I'm taking the minimal tilting complex of n. So the indices on n are changing here, but the indices on m are fixed. So on each line, I'm tensoring the minimal tilting complex of n with a fixed term of the other complex. In each column, I'm tensoring the minimal tilting complex of m with the fixed term of the minimal tilting complex of n. Okay, so each of these here is a tensor product of the minimal tilting complex of m with something else. So this is sort of the double complex. All the rows are complexes, all the lines are complexes. And now what we do is basically we take this double complex and we lump things together on the diagonal. Okay, so one term of the tensor product complex that we're getting in the end is going to be the direct sum of all the things sitting on one diagonal. So here you see, this is supposed to be a minus.
Right.
All the terms that are on this line that I just drew, the sum of the two indices is I plus j. On the diagonal just above, the sum of the indices is always going to be I plus j minus 1. And in the line underneath, the sum of all indexes is always going to be I plus j plus 1. Now, if you want to have the differentials between two of those terms, basically they're given by all the arrows going between two diagonals. Okay. So this is how basically you start from two complexes, you tensor them together into this huge double complex, and then you turn the double complex into a single complex. Yes?
That first j is also j minus 1, right, in the second row? Yeah, degree of C.
Wait, what am I doing here? Yeah.
In the second row.
Yes. Yeah. It should be constant.
Yes. Yeah.
Thank you. Okay, so why is this a good thing to do? Well, essentially, if you take this tensor product complex as a way of computing its cohomology and is given by the so-called Knuth formula. So concretely, what happens here is if you want to have the degree k cohomology of the tensor product complex of these two, then the Knuth formula abstractly tells you just that this is going to be just the sum over all I and j, that sum to k of the cohomology groups of the two complexes. Get h I of the minimal tilting complex of m tensor hj of the minimal tilting complex of n. But now we know that this here is only non-zero if I is equal to 0, and this here is only non-zero if j is equal to 0. So this here is just going to be isomorphic to m tensor n if k is equal to 0, and 0 if k is non-zero. And so this means that the minimal tilting complex of this tensor product is going to be a direct summand of the tensor product complex. Okay? So this tensor product complex, it doesn't need to be minimal, but at least we sort of have an upper bound for the minimal tilting complex of the tensor product that we want to study. It means that Cmin of n is a direct summand of Cmin. Are there any questions for that? If not, then I'll move on and tell you some applications of this technique. Work.
do you have a sense of like, have you done any calculations to see whether typically like this tensor product of minimal complexes is actually minimal, or if there's a big, you know?
I haven't done many explicit computations, but in whatever I've looked at, it looked like it's usually very far from being minimal.
Okay.
So it blows up quite a bit, but as I'll tell you later, there's a few things about it that you can control still. So, application 1. This is tensor ideas. And why don't I just start and tell you what is a tensor idea? So a tensor idea in rep of G, say. So it might be in rep of G. It might also be in tilt of G. So I give the definitions of this time. So this is a set of, well, either it's a set of tilting modules, or it's just a set of arbitrary modules, depending on whether or not you want a tensor ideal in all representations or in tilting modules, okay? And well, it's supposed to satisfy certain conditions. So when you're given two G modules or two tilting G modules, depending on which of the two definitions you're interested in, then firstly we want that the direct sum is supposed to be inside tensor ideal. It's called the tensor ideal I. So the direct sum is supposed to be in I, and only if both of the summands are in I. And secondly, if one of the two belongs to I, then also the tensor product belongs to I. Without any additional conditions on the second module here. So this is sort of a way of mimicking the construction of an ideal in a ring. It's just now you're given a category with the tensor product and you replace the multiplication with the tensor product. And you have this additional condition, direct sums, which makes things somehow more well-behaved. Okay, so just a remark, there is a way of classifying tensor ideas in the category of tilting modules by p-cardinalistic sets, which are some sort of combinatorial objects based on the p-canonical basis of Jolly Williamson and Simon Rich, which is something that is still very hard to understand, but at least there's some control over what the tensor ideas for tilting modules are. But so far there's sort of been very, very little research on what the tensor ideas in rep of G are. Mm-hmm. So basically we have this thing where tensor ideas are sort of controlled, and this thing where tensor ideas aren't controlled at all, and we can try to use minimal tilting complex to pass from one side to the other. So let me give you a lemma. Let's say we've given a tensor ideal in the category of tilting modules. Then well, we can look at the set of all G modules, say M, and we ask that all the terms of its minimal tilting complex belong to the given tensor ideal. So we ask that Cmin of Mi is in I for all I and Z. Okay. Then I claim that this is a tensor ideal. And the proof is fairly easy. Namely, we need to check two properties, and the direct sum property follows from the fact that if we want the minimal tilting complex of a direct sum, it's just the direct sum of the minimal tilting complexes. Okay, so if all the terms on one side belong to the ideal I, then certainly all the terms on the other side also belong to I, and then we know that I is closed in direct summands. So that means that basically that means that get precisely this condition that we're interested in. And secondly, we have that this follows from the fact that the minimal tilting complex of M tensor N is a direct summand of the tensor product of the minimal tilting complexes of the two constituents. So C min of M tensor plus C min N. Now, why does this work? So, by the way, this tensor product complex is constructed, each term therein is basically a direct sum of tensor products of things in the two complexes. So, if we assume that M belongs to I, then all the terms in C min of M belong to I, then so do all terms in the tensor product complex. And then if we go down to a direct summand, because of the first condition which holds for I, still all the terms need to belong to I. Okay, so this completes the proof of that thing. It's fairly easy. And so, as I said, this gives us sort of a way of starting from a tensor ideal in tilting modules and constructing a tensor ideal in the entire category. It is unfortunately not a complete solution to the problem of describing all the tensor ideals, and I'll tell you why not after erasing some more of what I wrote before.
So for SL2, we know the answer, is that right?
You mean all the tensor ideals in
Yeah.
FG? I'm not sure. So I think you mentioned to me at some point that Will Hardesty had worked on that.
Yes.
But I don't know if he if he wrote it down or if there's a preprint.
I have right up someplace.
Okay.
Yeah, sure.
I'd be interested to see it.
Okay,
Yeah.
that's fine.
But I don't think it's published.
Okay.
Okay, so basically, so we're given. Okay, so for any tensor ideal, I in tilt of G. This tensor ideal angle brackets I that we constructed is going to have what is called the 2 out of 3 property. So say 2 out of 3. And what it means is whenever you're given a short exact sequence with terms say A, B, and C, such that 2 of A, B, and C are in the ideal, then so is the third, and the third one is as well. Okay, So that means that, I mean, if A and B belong to the ideal, then C also belongs to the ideal. If A and C belong to the ideal, then B belongs to the ideal. And if B and C belong to the ideal, then A belongs to the ideal. This essentially comes from the fact that these minimal tilting complexes are somehow defined internally in a triangulated category. Like you sort of pass through the homotopy category when you're defining them. And so this 2/3 property is sort of a relic of this triangle rotation that you get in triangulated categories. And so this means that, next remark, basically this map that sends I to angle brackets I is a map from tensor ideals in tilt of G to tensor ideals in rep of G with the 2/3 property. Okay, so it's also going to be an injective map because whatever tensor ideal you start from, you can just intersect it with the category of tilting modules, and this sort of gives you a right inverse for the map you're looking at. It turns out that it's still not surjective, so this is in general not a bijection. Constructing a counterexample is a bit technical, so I don't want to go into the details. I just want to tell you that basically it's a parallel theory for all of this, where you replace the algebraic group by a quantum group by a group of unity. And this is sort of a situation that is slightly more well behaved in the sense that, for example, in that case, we know the composition factors of the standard modules, which in positive characteristic is a very hard problem. It sort of was expected to be solved by Lustig's conjecture, but then counterexamples were found by George Williamson. Very surprisingly for many people, I think. So this theory in positive characteristic is much harder than many people would believe. But anyways, like if you replace the group by a quantum group in the setting, then this turns out to actually be a vector. Okay, so any questions about this before I move on to the next application? So, application 2. It's going to be about blocks. And I think this is what I announced in abstract. Basically, there's this very useful notion of a block in representation theory. So usually if you look at a category of representations, it's some sort of big abelian category, but often it's sort of too complicated to understand the entire thing at once, but it often sort of breaks up canonically into smaller pieces that we then call blocks. Okay, so this is a very common field of study for representations of groups. But usually when you're interested in the monoidal structure, then the block structure doesn't really help you, because if you take two representations, both coming from a fixed block, and you tensor them together, you're going to get indecomposable direct summands that are sort of all over the place in different blocks. So these two notions of a block and sort of a monoidal structure on the category are usually not really compatible with one another. And
Sorry, I
yes.
have a question coming back to this.
Yeah.
So suppose you take KB tilde,
yes.
which is triangulated.
Yeah.
So do you think it is possible to classify big tensor ideals in that situation?
I wouldn't know exactly. So, I mean, I made some computations in the quantum case for SL2.
Yeah.
And there it's easy because it's easy to write down the submodule structure for all tilting modules. It's basically the same as tensor ideals in the category of tilting modules. Otherwise,
well, let's say you can do that. Then you can push it over to DB rep.
yes.
Okay. And then if you knew that, let's say you knew the answer, do you think you can push the answer down to rep G? It's worth a try. Yeah.
It's not completely obvious. I think there's different ways of trying to construct tensor ideals in rep G from tensor ideals in the derived category or vice versa.
Right.
And it's not clear what's the correct construction to me.
Okay.
Okay. So what I want to talk about is basically how we can use the tensor ideals that are just defined to somehow make make the block structure of the algebraic group compatible with the monoidal structure, but we have to pay a price. We have to take a quotient by a tensor ideal, so we sort of forget about a part of the module. But I guess that's always the way it works. You know, if you want to get something better, you have to pay a price. Well, before I tell you how this works, I have to tell you what the blocks look like. So we need a little bit more notation. We're going to write W for the Weil group. Oops, group of phi, and we're going to write rho for 1/2 times the sum of all positive roots. And we're also going to assume from now on that P is greater or equal than H, which is the constant number of the root system, which is defined as the maximum of all scalar products of rho with positive co-roots, and then you add 1. Okay, so definition: if we're given two weights lambda and mu in X plus, then we say that they are linked, and we write that, well, we just write an equivalent symbol lambda tilde mu. If and only if, this is the definition, if and only if lambda is equal to W of mu plus rho minus rho plus P gamma, some element of the Weil group and some element of the root lattice. Okay, so essentially what this means is, if you only look at the first part, this means that lambda and mu are in the same orbit under the dot action that we also already saw when he was describing the blocks of category O last week. But now we're also allowing ourselves shifts by p-th multiples of elements of the root lattice. Okay? And now there's a theorem, which I'm not sure what the completely correct attribution would be, but I think it's good to say Andersen and Janssen. And it says that two simple modules are in the same block of the category type of G, if and only if the weights are linked. If they are in the same block, then the weights are linked. So, if L lambda, L mu, the same block, are linked. The converse is not true in general, but so in most cases the converse is actually true. There's a few sort of more degenerate blocks where different blocks form a union of linked union equivalence classes. Let's just fix a set. There's going to be a set of representatives for the equivalence classes. So let's say for mu in X such that 0 is less or equal lambda plus mu plus rho. Check less or equal than P for all alpha plus. And it says this is a system of representatives for the linkage equivalence classes. And so I'm calling this C bar because there's also going to be a set C. And this is going to be basically the same condition, but we replace the less or equal signs by strict inequalities. Okay? So we look at all the mu in X, that 0 is less than mu plus rho alpha check is less than P for all class. And well, as you can maybe guess, the bar on top is sort of supposed to evoke closure, which doesn't really make sense in this setting because these are both discrete sets. But the way you would usually do this is that you would define them as subsets of the Euclidean space and then intersect with the weight lattice, and then it sort of makes sense. But I didn't want to bother with that, so here we go. So we have two sets, and one of them is a system of representatives for the linkage equivalence classes, and then there's another definition for lambda in C bar, the linkage class. Of lambda is going to be the Serre subcategory of all representations that is generated by all simple modules in the linkage equivalence class of lambda. So we are going to write this as rep lambda of G, and it's by definition what is generated by all L of mu, where mu is an X plus and mu is linked to lambda, and it's the Serre subcategory generated by all of these things. So it's the smallest extension closed subcategory containing all of these samples inside rep of G. And with this definition, this theorem of Anders and Janssen tells us essentially that the category rep of G breaks up into the linkage classes. So you can write it as a direct sum of all mu C bar of rep mu G. Okay. And so these are sort of like a first approximation to the blocks, as I said before. And furthermore, there's a statement that tells you that if lambda and mu belong to the set C that are wrote above, so sort of the interior of the set C bar, then there is a translation functor T lambda mu, which is an equivalence from rep lambda of G to rep mu G. So these are equivalent as a beginning categories. Okay. So I've drawn a picture over there to show you all this Weil group combinatorics in the case of G SL3 of K when the characteristic P is equal to 5. Okay, so you can see down here, this is the type A2 root system, and the red weight here, which I'm just pointing at, is the 0 weight. So if you just look at the orbit of 0 on the dot action, then you get the points here. So the intersection of these three lines down here, this is minus rho. If you look at the rho shifted action of the finite Weil group, then you get these 6 points here. But now you're also allowed to dilate by a pth multiple of a root. So let's say if you take the pth multiple of this highest root in the root system, and we shift upwards by a factor of 5. So you get 1, 2, 3, 4, 5, we end up here. So for each of these points here, given by the action of the finite Weil group, we can also shift it up by a factor of 5 times the highest root. And so all of these things here would sort of, they will all be in the same linkage class, the weights. And I've drawn these additional lines. Maybe you can see that basically you can also get these additional points in the same equivalence class by reflecting across the lines of the picture. So if you take this point, you reflect it up across this line, you end up with this point up here. And essentially, I haven't been telling you up here, but there's an action of another reflection group involved, and this is the affine Weil group, which is the similar product of the finite Weil group by the root lattice. And basically the definition of the linkage classes means that it's just the same as saying things are in the same orbit under the action of the affine Weil group. If you dilate the action of the translation part by a factor of p, and if you shift the action of the finite Weil group down by rho. Okay. Right. Any questions about this? If not, then I'm ready to state the few final results about how the blocks are related to tensor products. So which part do I erase? This one.
So are you going to assume that the prime is large enough, like it's bigger than the coxswain?
Yes, I think I said this when I set up the
Oh yeah, there it is. Okay. Okay. So that guarantees the existence of the regular
Yes,
weight.
so essentially this condition here is to ensure that the weight 0 lies in the interior of this region that we fixed. So it lies in C and not in C bar. Basically the set C bar is everything on the boundary of this bottom triangle. The set C is everything in the interior of the triangle. Okay, so in order to compare blocks with tensor products, we're going to look at a specific tensor ideal in the category of tilting modules and then carry it over into the full category of representations. So a tilting module, say M, and we can always write it uniquely as a finite direct sum of indecomposable tilting modules. So it's going to be T lambda direct sum M lambda for certain multiplicities M lambda, okay? And we call it negligible. If M lambda is equal to 0 for all lambda in the set C. Okay, that means we are going to be allowed indecomposable direct summands of highest weight, sort of on this top boundary line and above, but not within the interior of the bottom triangle. Okay. So if this is the case, then we're going to write M in N. So in other words, we write N for the set of negligible tilting modules, and then N is a tensor ideal in tilt of G. So this means that if you take this angle brackets construction, then you also get a tensor ideal in rep of G. And since we're looking at tensor ideals, we can define quotient categories. So first we can look at rep of G modulo angle brackets N, and we can look at, so this I write as underline rep of G, and then we can look at tilting modules modulo negligible tilting modules, and this is what, this has been studied a lot before. It's called the Valinde category. Tilt of G modulo N. These are two categories, and we have a canonical quotient functor from rep of G into this rep of G underline, and we're going to write rep underline 0 of G for the essential image. Of rep 0 of G under the quotient functor. Okay, so this is the objects are, it's the full set categories. Objects are all the things that are isomorphic to something in the principal, like in rep 0 after we go down to the quotient. So rep 0, this is the leakage class of 0, usually called the principal block, because this is actually a block, it's not a union of blocks. And now the main theorem comes in two parts. So first, if you look at this rep underline 0 of G, so the image of the principal block in the quotient category, then this is closed by tensor products. Rep G underline, and then secondly, basically the second thing I want to say is that this here controls the entire structure of the quotient. So if you want to understand tensor products in the quotient, it's actually enough to understand this here. And the way we do this is we say that there's equivalence of k-linear Neumann categories between the full quotient category, the underline G, and the principal block in the quotient, and then we take an external tensor product of this with the Berlin category. And so the Berlin category is a semi-simple tensor category where all the home spaces are one-dimensional and all the multiplicities of taking tensor products are actually known by a combinatorial formula. So this is something we really understand, which means that basically all the tensor product information up to direct summands in angle brackets n is really going to be encoded in this principal block. And taking tensor products in the principal block sort of makes sense by the first part of the theorem. This sort of works.
Any questions for the speaker? Let's thank Jonathan again.